I'm Bahman. I'll talk about the sketching techniques for real-time big data. So sketching is a set of techniques, and this is a pretty mathematical topic. So I decided that we would just go through 3 concrete applications, and then through the applications we will see how sketching works. So the applications are from security, semantic analytics, and reputation systems. So let's dive into the first application. So all of us have had to deal with these password selection policies whenever we want to create an account online. So these policies are like the length of the password should be at least 8. It should include both letters and numbers, both lower and uppercase letters. It should have some non-alphanumeric characters. It should have a number between the first and last character. It shouldn't be your dog's name. You should change it once a month. It's just like a whole list of them. And these rules have unintended consequences. Like if you require a minimum length on the password, what the users do is that they use dictionary words, or they write down their passwords because they want to remember the password. Or if you require that the password includes special characters, then what the users typically do is that they have these simple replacement rules, like replacing E with 3, A with @, and they just use these to come up with some special characters. And if you even forbid these simple replacements, then what users do is that they map characters to a small set of concepts like hash and pound, hat and top, and so on. So at this point, these rules have become like these policies have become like a cat and mouse game between the systems administrators and the users. So the systems administrators want to ensure security, the users want to ensure usability. What is sacrificed here is for sure is usability, but actually there is no guarantee that the security is ensured. There was an article in the New York Times like 2 years ago, which was exactly on this topic, and there's absolutely no guarantee on whether or not these rules actually guarantee security. So then why do we have even all of these rules? So these rules are all about protecting the user from a specific kind of attacks called statistical guessing attacks or dictionary attacks. So how these attacks work is that the attacker has a list of passwords, has a dictionary of passwords, and for each password they also have the frequency by which the users typically choose that as their password. And then what they do is that they go through the list of passwords in the order of their frequency, in the order of their popularity, and try to crack the user's accounts. So it's all about the frequency and popularity of the password. But then a simple question is, if it's all about the popularity, then why not just measure the popularity of the password? So here's a very simple way to do it. Just have a popularity oracle. It's just a simple hash table, which maps a hashed version of the password to its count. And then whenever a user arrives, wants to choose a password, just look up the password in the hash table. If the password is popular, don't let the user choose that password. Ask him to choose another password. If it is not, then just let them choose a password. So, and as an example, let's say you have 100 million users on your website, and you limit the popularity of each password to 100. So that means that an attacker who even knows exactly the most popular password can only crack 1/1 millionth of the accounts. But this same attack in 2006 cracked 20.22% of MySpace accounts, and in 2009, late 2009, cracked 0.9% of RockQ accounts. So what is the problem with this simple way of doing it? The problem is that if you want to construct the hash table that I just talked about, this oracle doesn't allow any salting. So if you know about salting, you know that each entry is salted so that the security of each entry is improved. If you don't know about salting, it doesn't matter. But the whole point is that because you want to keep the count of each password, by definition, it means that you have to aggregate, and you cannot do a per-entry salting of the password. And what it means, it's very simple to understand what that means. It means that if this table gets compromised, if it's stolen, then the attack is actually optimized. Like the attacker knows exactly the frequency of each password, so he can go through the optimized order. So this is a problem with this oracle. So let's see if we can fix it. So what are the requirements for a good oracle? A good oracle should have these 3 properties at the minimum. It should keep the counts of the passwords without keeping the passwords themselves. But at the same time, it should allow for quick updates. Whenever a user arrives, chooses a password, that password should be reflected in the Oracle right away. You don't want to start protecting the user a week from the time that they created the password. And it should also allow for quick queries. Like whenever the user chooses a password, you should be able to quickly ask the Oracle, is this password popular or not? And it should be able to quickly tell you if it is. And if it is, you don't let the user choose it. If it's not, then you do. So let's see if we can do this. So here's a candidate Oracle. We call it candidate magic Oracle. So it's just a simple table of counters, D by W, D rows, W columns. D is a small number, like 5, 10, and W is a bigger number, like 10,000, 100,000. And what do we do? So the first user arrives, and all of these counters are initialized to 0, and they are supposed to keep track of the counts of the passwords for us. Let's see how they do it. So the first user arrives, he chooses his password. What we do is that we hash this password to one counter in each row. Exactly one counter in each row, we hash it. And then we increment those counters, so we get this table. And then another user arrives, he chooses a fancier password. Then we do the same thing. We hash this password to one counter in each row, and we increment those counters. So now notice that this one, that one, and this one are now keeping the counts for this password. And that guy, that counter, and this counter are keeping the counts for the first password. Now let's say the third user arrives, and he chooses this password, diamond password, and we hash this password again to one entry per row. But now something happens. Now in the first 2 rows, this password, the bucket that this password is hashed, is colliding with the bucket that some of those previous passwords had been mapped to. So these counters were supposed to keep counts of these passwords, but now we have these collisions. So how does this Oracle deal with the collisions? So the answer to that question is that it just doesn't care. So the way it does it is that it just goes ahead and increments those counters just like nothing happened. And it ends up with this table. And then let's say another user arrives, he chooses the same password as the first guy. Again, we hash it to the same buckets as the first guy. We increment those counters. And now let's say at some point we want to query and get the count for some password. Let's say this last password. Again, we hash it to the same exact buckets. And what do? We take the minimum of those counters, the minimum value. Notice that this counter here, we had a collision. So that counter doesn't have the right value of the count for this password. But these 2 counters do. So if you take the minimum, then we are fine. So does this generalize to the general setting? The answer is yes. So there is a theorem which says if you choose the values of D and W properly, it leads to very small amounts of error with very large probabilities. So with a very large probability, we'll have very small error. And formally, if you choose any 2 numbers, epsilon and delta, small numbers, less than 1, let's say, and you choose W and D according to those formulas, then you get at most epsilon error in the frequency with probability at least 1 minus delta. Let's see an example of this. So if you choose W to be 270,000 and you choose D to be 14, then the error that you get in frequencies is less than 1 over 100,000 with probability 1 minus 1 over a million. So it's a pretty accurate oracle. And what's the magic in this oracle? The magic is that this guarantee that we just saw, it holds independent of the number of passwords. So as an example, it can fit the approximate counts, but these approximations are really good approximations, of the counts of 100 million passwords in less than 4 million counters. It kind of looks like magic. So as a result, it's also pretty memory efficient. So let's see what happens if this oracle gets stolen. If this oracle gets stolen, well, we just saw that if you choose D and W large enough, then you can guarantee very, very small amounts of error. Well, the answer to this is that, well, don't choose D and W that large. Choose them small enough. It's actually a pretty counterintuitive idea if you think about it. It says like, it chooses D and W, the values of D and W small enough so that you can guarantee a minimum rate of false positives. Okay, so a minimum error rate. So what does this mean? This means that it has 2 implications. The first implication is for the user. So what happens for the user if there is a minimum amount of false positives? So the user, what happens for the user is that every now and then the user chooses a password. The password is not really popular, but the oracle thinks that it is popular because of the collisions that it has had with other passwords. So it asks the user to choose another password. Big deal. But for the attacker, this turns the oracle completely useless, especially noting that the attackers already have approximate counts of these passwords. So it also makes it pretty secure. So it's a pretty simple scheme for password selection. I'm not sure if this scheme has been implemented anywhere. This was proposed by two folks from Microsoft Research and a professor from Harvard. I'm not sure if it's been implemented anywhere, but if it is not, I think somebody should go ahead and do it. So this article that we just saw, what are the properties that it had? It had 3 properties. The first property was that it used a very small amount of memory. Just like I said, it can fit a lot of counts in a very small number of counters. And it also doesn't keep the passwords themselves, so that saves memory in terms of like keeping those strings. So it only remembers what matters. And at the same time, it allows quick updates and quick queries. Okay? Well, this is exactly the definition of a sketch. This is what a sketch means. Let's see a simple example, like the simplest examples of a sketch. So let's say you have a stream of numbers, A1, A2 through AT, some numbers like 1, 2, 100, whatever. What is a sketch for sum? Well, the sketch for sum is just a running sum. You just keep this summation of the numbers that you have seen so far. Whenever you see a new number, just add it to this number that you have so far, and that's the updated value of sum. And whenever you want to see what the sum is, you just read off this number. What's the sketch for average? You just keep 2 numbers, running sum and count. Whenever a new number arrives, you increment the count, you add that number to the running sum. Whenever you want to see what the average is, you divide this running sum by the count. And there's a very nice cognitive analogy for sketching. The analogy is that we as humans are going through a constant stream of sensory observations at all time. But we somehow manage to only remember parts of these observations and some smart combinations of these observations. And we still manage to function properly with that, with a small representation of all these sensory input that we are getting. So in a sense, all of us are doing sketching in our brain. So this is a cognitive analogy for sketching. So now that we have seen one application, we know the definition, and we know that everyone is doing it. Let's see the second application, and it's in semantic analytics. There's a wide range of applications of sketching and semantic analytics, so I start with an example, sentiment analysis. So what does sentiment analysis mean? It means that for a word, you have a corpus. It can be, say, the stream of tweets, and you want to see if a word has been talked about more in a positive sense or a negative sense in this corpus, in this stream of tweets. Like the word can be a product that has been just shipped. You want to see if people are liking it or not liking it. That's what sentiment analysis means. Let's see one example of this. Let's say these folks are talking about this new awesome phone that has just come out called My Phone. And we want to detect if the sentiment among these people about My Phone is positive or negative. Let's see if we can figure that out. And I'm not even showing you the whole messages that these people have, the whole thing that these people have said. So I'm just saying from each person, I'm just showing 2 words. From this guy is saying blah, blah, my phone, blah, terrible. This guy is saying blah, bad, blah, blah, my phone. This guy is saying excellent, blah, blah, my phone. This guy is saying like my phone, whatever. This guy is saying my phone, great. This guy is saying blah, nice, blah, blah, my phone. And this guy is saying my phone, blah, blah, good. So what is the sentiment in this? So these 2 guys, this guy and this guy, most likely are saying bad things about my phone, because this guy is saying my phone, blah, blah, terrible. And same with this guy. So these 2 guys most likely have are saying bad things about my phone. This guy, and these 2 guys are most likely saying positive stuff about my phone, because one of them is saying like my phone, blah, blah, great. Like it can be like, I know, my phone is a great phone. This guy is saying, I know, a nice feature on my phone is whatever. And this guy just doesn't care. He's just saying that my phone, whatever. He's just probably saying that, I know, my phone has an antenna or something. So the overall sentiment in this, I think we all agree that it's positive. So these 2 guys are negative. This guy doesn't care. And these 4 guys are positive. So overall, it's a positive sentiment here. So how did we do this? I didn't even show you the whole messages that these people had posted or whatever we're talking about. So what we did was that we measured the co-occurrence counts of my phone and the positive words of the English language, like good, nice, great, and also my phone and the negative words of the English language, like bad, awful, terrible. So the whole analysis that we just did was based on these co-occurrence counts. And the fact of the matter is that these co-occurrence counts are one of the most fundamental constructs in semantic analytics and natural language processing. They have applications from statistical machine translation all the way to speech recognition. But to enable these applications, you would need to find the co-occurrence counts between all pairs of words in your corpus. So what does that mean? It means that you have a large corpus of documents. It can be the tweet stream. It can be the web, like all the web pages. And you have a vocabulary of words, W1 through WN. It can be the vocabulary of the English language, in which case N is like in the hundreds of thousands. It can be the web, and these words can be like n-grams of different sizes. So it can be like in the billions. And what is the goal? The goal is that for any two words in this vocabulary, we want to count the number of documents that these two words have appeared together in that document. Okay? So that's what a co-occurrence means. Well, I mean, this seems like an easy problem because it's just counting, simple counting. But the problem with it is that there are too many unique word pairs. So let's see an actual example. This is from a research paper from 2010. A very small corpus, less than 600 megs. It has 78 million words. It has 63,000 unique words, but 120 million unique word pairs, which is like a factor 2,000 more than the number of unique words. This is a pretty small corpus, but actually when as the size of the corpus gets larger and larger, this problem gets worse and worse. It is not hard to see why is that, because one of them is growing like order n, the other one is growing like order n squared. So as the corpus gets larger, this problem gets worse. So what is the solution for the problem then? Well, the first problem is just to use Hadoop. Okay? We just use Hadoop. We throw a 50-node cluster at this problem. We compute all the co-occurrence counts exactly. I'm sure all of you can either know or can easily figure out how to write this, how to solve this problem in MapReduce. If you want, you can also look at the book by Jimmy Lin on text analytics in MapReduce, which has a whole section on this problem. So that's one way of doing it. But what is the problem with this is that the problem is that it's too inefficient. So you have to have all of these word pairs, and then you have to write them on the disk. You have to communicate them on the network. It is just too inefficient. So is there a better way? The better way is that the count minute sketch that we just saw in the password setting is useful here as well. So the basic idea is that we use this sketch to track the counts of the word pairs. Okay? Let's see how we do it. So we start with our initial count minute sketch, a table of counters, each initialized to 0. Then we get this first document. Let's say it's a tweet. So the tweet is, how do you shoot a yellow elephant? So then what we do is that we find all the word pairs in this document. And let's say we only care about the non-stop words. So we only care about the words shoot, yellow, elephant. So what are the word pairs in this document then? The first one is shoot and yellow. Okay? And we do exactly what we did with the passwords. We hash it to one entry in each row. We increment the counters. We get this table. Then the next pair, shoot an elephant. We hash them. We increment the counters. Then the next pair, yellow and elephant, we hash it, we increment the counters. So we just continue doing this with all of the documents that we have in our corpus. Okay? And the nice thing is that you can do this on the fly. Like as a tweet stream is coming in, per tweet you can do this. So, and let's say if you get back to the sentiment analysis example, let's say we want to figure out if people are talking positively about my phone on Twitter or not. So what do? We have built this sketch. So our customer comes in. He says, I want you to tell me what is the sentiment about my last product, my phone. So what we do is that we just query this sketch that we have with these pairs of words. My phone good, my phone nice, my phone bad, my phone terrible, and so on. The my phone and the positive words, my phone and the negative words. And then we combine these co-occurrence counts in some way to figure out the sentiment, just like we did in the example that we did at the beginning. So what is the gain that we achieve by using the second solution compared to the vanilla Hadoop solution? Well, the first gain is that we don't store the word pairs themselves, and that results, and that plus the efficiency of the counting sketching, keeping the counts themselves, results in a lot of space gain. Like in an actual study of this technique, of this exact same problem, the space gain that was achieved was 30x. Okay? And the corpus size was 37 gigs, which is not that big, even though it can have a lot of word pairs. And with 30x less space, they could get almost 0 error rate. Okay? And notice that, as I said, when the corpus gets larger and larger, the problem gets more and more serious, which means the space gain becomes more, larger and larger. And what does this 30x mean? It can be the difference between a 30-node Hadoop cluster and a single commodity machine under your disk. So that's what it means. So let's now see the third application. So the third application that I want to talk about. So the first two applications that we just saw, there were other ways to deal with the problem. Like in the first application, you could still go on with the rules that you have. In the second application, you could use your 50-node Hadoop cluster. You could do something. In this third application that I'm going to talk about, for the goal that I will say we have in this application, it is just impossible to do it without having the sketching approach. So let's see what it is. So what is the motivation for this problem? The motivation is coming up with a network recommendation system. So recommendation systems and reputation systems are very closely related. Like a good recommendation for you is another user who has a high reputation for you. So if we forget about the personalization, it just becomes a reputation problem. And it's easier to talk about, so I'm going to just go with the reputation scenario, even though all of the techniques that I'm going to talk here, all of the algorithms and results, apply to recommendation systems as well. And as our network reputation system, we use PageRank. So PageRank is a very well-known network reputation system. It was devised by Larry and Sergey. And it started what we know now as Google. And the basic premise in Google, the basic premise in PageRank is that it treats each link in the network as an endorsement. So a node is highly reputed if a lot of other highly reputed nodes link to it or endorse it. Like in this example down here, this guy, the yellow guy, has a high reputation. Why is it? Because a lot of people are pointing to it, are endorsing it, and some of them have pretty high reputations. Or this guy is actually interesting. Like this red guy, no one is pointing to it except this yellow guy. But this yellow guy himself, like alone, has a very high reputation. So that gives a lot of reputation to this guy as well. So that's how the PageRank, the basic premise in PageRank works. So let's first look at our goal. So now that we know the definition, we have an idea about what PageRank means, let's see what our goal is. Our goal is to compute the PageRank values on the fly. Okay? So it means that we have a network, we have a graph, and the network is changing over time. What is a network? An example of the network, the nodes can be the nodes on a social network, the users on a social network. The links can be the friendships, or the links can be even social events. Like, what is a social event? Someone tweets something, there is a link in the tweet, someone else click on the link. We can consider that click an edge from the person who clicked on that link to the person who tweeted it. Okay? So if you imagine these social events, these events happen at very, very high rates at a network like Twitter. And the goal is to maintain an accurate estimate of the PageRank of all the nodes as soon as any edge arrives. Okay? So it's a pretty challenging problem. Like you have hundreds of millions of users. You have this very high rate stream of changes to the network that's happening if you consider the social events. And you want to keep all of these 300 million, or whatever 100 number of millions of users updated constantly. So now that we know the problem, let's look at a little bit deeper into PageRank and get a better sense of what it means. So there is a random surfer interpretation for PageRank. So the random surfer interpretation is that there's a random surfer, there's a guy who is walking on the network, and he's walking in this specific way, that at each step, there's a probability epsilon, which is like 0.15, 0.2, and with probability epsilon, at each step, he jumps to a completely random node in the network, okay? But if he doesn't jump to a random node in the network, then what he does is that he just gets a uniformly, like a random link, random outgoing link from the node he's currently on. So what it is modeling is that the user starts on some random web page, and then there are some links in the web page, and he chooses one of those randomly. He clicks on it, he goes to that page, and then there are some links in that page. He clicks on one of those randomly, and so on. And after some time of doing this, he gets bored, so he jumps to a completely random node. So that's what it's modeling. And PageRank is a stationary distribution of this walk. It means if you do this walk forever, what is the fraction of time that you spend at each node? That's the PageRank of that node. So let's see an example of this quickly. Let's say this is our network. The random surfer starts here at node 3. Then from the nodes 2, 4, 6, he goes to node 6, just randomly, and then maybe to node 7, and then node 8, and then he gets bored and jumps to node 10. Okay? So this is how it works. So what are the computation methods for PageRank? There are two basic methods of computing PageRank. Like there are two families, actually. There are two families of computing PageRank. One of these families is based on techniques from linear algebra, the simplest of which is power iteration. I'm not going to talk about it, but it's an iterative method based on matrix multiplications. And the second method is a Monte Carlo method, whose main idea is to just simulate the PageRank random walk for a while, and then use the empirical distribution as the estimate for PageRank. Just see how many times you hit each node, and then just use that as your PageRank approximation. The problem is that neither of these two methods can be efficiently done on the fly. So how do we achieve the goal that we talked about in the beginning? So here's the sketching idea. The idea is that if you look at the PageRank random walk, if you do it for a long enough time, how does it look like? You start at some node, you go for a while, and then you get bored, and then you jump to another node, and then you go for a while, you jump to another node, you go for a while, and then you jump to another node. So if you do this for a while, you will have these short walk segments hanging from each node, kind of, okay? So you have these dangling walk segments which are hanging from each of your nodes. So the sketch just uses that view of the PageRank random walk. So how it works is that I'll tell you what the sketch is, and then we'll see an example of it. So it stores R random walk segments. R is a small number. It can be even 1. Okay? It can be like larger, 3. Random walk segments at each node, and each of these random walk segments, it starts at that node and continues until the first time that the walk wants to teleport, and just quits at that point. It doesn't teleport, it just quits. Okay? And the update here is that whenever a new edge arrives to the network, we only update the walks that actually need an update. So what does that mean? When a new edge UV arrives at the network, we only need to update the walks that pass through the node U. And each of those walks needs to be updated with probability 1 over degree of U. What does it mean? So let's say that our node U had like 3 edges before. So when we arrived at this node in this walk before, with probability 1/3, we took each of these edges. Now, the node U has another edge, so it has 4 edges. So now there's a probability of 1 over 4 that when we get to this node, we'll choose this new edge. And if you do that, then the walk needs to be updated. It needs to be rerouted. Okay? So that's what it means. But any other walk that doesn't pass through U is still a proper random walk. It doesn't need any updates. So let's see how it works. So let's say we have this huge 3-node graph, and then we have done 10 random walk segments starting at each node. So let's look at the, say, first random walk segment is starting at node 1. It starts at node 1, goes to node 2, back to node 1, 2, 3, 2, 1, 2. It's just a random. It's an actual simulation. So it's just this random walk, and then at that node 2, the final node 2, like this guy, it has just teleported, so we just quit it. So these are the random walk segments. So we just store these, okay? And then let's say we get a new edge from node 1 to node 3. Then some of the walks will need to be updated, the red ones, okay? But as you can see, a bunch of them don't need any updates. So why is that? Like some of them don't even pass through the node 1, like this guy, 2, 3. It doesn't even pass through the node 1, so it doesn't need any updates. Some of them do, but they just happen to make the same choice. They just happen not to choose to go to node 3 after node 1. So they're just fine. And the key insight here is that in the network, most of the edges miss most of the random walk segments that we have. That's a key insight in one sentence. And another insight here is that as the network gets larger and larger, this effect actually becomes more and more pronounced. So let's see how it works. Let's say this is our graph. Those are some of the walk segments that we have done. This guy is a node on one of these walk segments. He gets a new edge. And then with some probability, we need to update this. Know that when this new edge arrives, none of these random walk segments care about it. They are just fine. I mean, they're just still proper random walks. But this guy does. And we need to update it. So we update it. We throw away this last part, and we reroute it to use this new edge. Okay? So this is how the algorithm works. And you can formalize what I just said, the insight that I just said, and something really counterintuitive happens. What happens is that as the network grows, the marginal amount of work that you need to do to keep all of the walks updated decreases. So as the network grows, it becomes easier and easier to do this computation on the fly. And the formal theorem is that in expectation, the amount of work that you need to do when your network has t edges is proportional to 1 over t. So if you bootstrap this computation, this sketching scheme I just talked about, at the time that your network is already has a lot of edges, then this t in the denominator is already really large. So this number is really small. Then you can actually do this computation on the fly, even per social event. And this is just impossible with the techniques that we just saw. This is just impossible if you don't adopt this way of thinking about the problem. So now let's look at the conclusions. So we talked about the sketching, its applications, some of its applications. So the main question here is, why do we even care? Why should we even care about the sketching? So one reason is that it provides a different view of thinking about and doing analysis of large data. Like instead of these big and bulky jobs that we have somehow become used to, it provides this way of doing analysis very nimbly and very efficiently on the fly. So instead of like waiting for a whole day, getting all of your tweets, running a big 50-node Hadoop cluster on it to get your results, your sentiments, you can just have this little sketch in your memory on one machine, just like we saw like in the sentiment analysis, it was giving you a 30x space reduction. So just use one machine, just keep this little sketch in the memory. Whenever something arrives, just quickly update that sketch. And whenever you want to get the result, just quickly query that sketch. You don't have to wait, you have a 30-node cluster. So it is much faster, it is much more elegant, it is much more, it gets you the results quicker. And it also has for those of us who care about the business aspect, it has a direct impact on the reduction of your data infrastructure cost. If you are using cloud, like Amazon, then you're paying for the computations that you're doing and for the network communications that you're doing. I didn't get into the network communication, but that's another aspect that sketching techniques optimize for. So they optimize the network communication as well. So it directly brings down your cloud data infrastructure costs. And if you have your own cluster, well, if you don't have a cluster, well, then maybe if using these techniques, you don't need to have one. But if you already have it, then they allow you to do a lot more with that cluster. And yeah, I mean, you don't, it decreases the capital expenditure that you have to have for paying for these clusters. And also you may not need like a lot of operations people to take care of those clusters. So how about the errors? Like one of the problems that people seem to be obsessed with is errors. They're like, oh, sketching gives us errors. So it's like we are afraid of them. So there are 2 points about this. The first point is that these are not like hand-wavy method that we just like do some sketching and then we cross our fingers that, oh my God, I hope there's not any error. No, there are like very strong mathematical guarantees behind both the rate and the size of the errors. Just like we saw in the case of the count in a sketch that we had, if you remember, we had those 2 numbers like epsilon and delta. That's a very universal theme in all the sketching techniques. So there are strong mathematical guarantees behind them, first of all. In many of the things that we don't have any mathematical guarantees and we don't seem to care about it. In this case, we actually do have mathematical guarantees and we seem to be worried about it. So that's the first thing. And the second thing is that as we saw like in the password case, both the probability and the amount of errors that you get are really small. So if you want to make any, like people talk about making business decisions based on analytics results and so on. So if you want to make any meaningful decision based on some analytic result, and you cannot make that decision based on a result which has less than 0.0001% error with probability 0.99999, if you cannot make that decision with that result, then most likely you are much better off not making that decision at all. So, I mean, there's this obsession that I think folks have to get over somehow. So, and then what's next in sketching? So I talked about some of the works that have been done in sketching, and what is next? First of all, there's a lot of applications that these techniques enable. Like in security, I talked about a small application. Social media analytics, I talked about 1 or 2, like both sentiment analysis and the recommendation/reputation system. Recommendation systems. In sensor networks, like sketching techniques are a very good way of doing sensor networks and also mobile applications, intelligent mobile applications. What is the reason? The reason is that you can have these little sketches on your mobile device or on the sketch, and whenever you get new data points, which can be like sensor readings or it can be like whatever that the mobile device is getting from whatever data, you quickly update this local sketch that you have, and every now and then you send this sketch to some server, to some central server, and you do some more computations there. And there are sketching techniques designed for exactly this type of application. So, and they take care of both the amount of computations and the amount of communications and the memory. So there are a lot of applications sitting there. And the math and the algorithms are there already. They are pretty rich, both broad and mature enough now. Like these techniques started in the 1980s. And then they started to in the algorithms research community. And then in late 90s, they started to catch people's attentions. There was this paper by 3 algorithmicists which won the Gödel Prize, one of the most prestigious awards in computer science. And then that started to get people's attention. And then in 2000s and 2010s, these techniques have been very, very heavily worked on by some of the best computer scientists in the world. So they are very broad and very mature now. And so the math and algorithms are there. So what is needed now? Well, for all of us, first of all, I mean, it's needed that we learn more about these techniques. And then we need some technologists to go build systems based on these techniques. As I said, they are now both broad and mature enough that they can be very well used for across a variety of applications. So we need technologists to go build these systems. Some systems that already exist, which use these techniques to a limited extent. But there is a lot more potential there. And then we need entrepreneurs who go and build products based on these techniques. And then for the big business leaders, it is needed that they start to learn about these techniques and they start to get used to them and start to adopt them and start to have their businesses benefit from these techniques. Just like I said, that you can benefit in your data infrastructure costs, in the speed of your analytics, a lot of different benefits that you can have. So this is, I think, what is next about sketching. And if you're any of these people and you would like to get in touch, I'm holding my office hours at 2:20 today. And also feel free to email me. Thank you.